in this simple example, we're given a single loop circuit that contains a voltage source that changes with time, and we're given the time function, or the voltage function in terms of time, and it's connected to an inductor of 100 millihenry, which is simply just 0.1 henries. Okay, and of course what we're being asked to compute is, well, we're given the voltage, so we're being asked to compute the current, the power, and the energy, and these are basically the equations in here. And we're also given that initially there was no current, basically there's no energy stored in it initially. That's what this assumption assumes in here. The current at 0, which is our initial time, is just simply 0. So if I assume that the voltage across it is in the same direction as the voltage source, and the current is actually flowing through it that way, so for passive sign convention purposes, the I is hitting the positive, so we just use the positive in everything you see here in red. So that basically tells me it's just a simple application of this particular equation. So I of t is just simply, well, the integral of 0 is 0, so it will be 0 before. Initially, there's nothing anyway, but initially there's nothing happening before time 0. And afterwards, what we need to do is we need to apply these equations. So afterwards, I of t is just simply, well, we have to do 1 divided by L, which is 0.1. And the whole thing here is just simply 10 times the integral from t0, which is basically 0, all the way to t. And then what we do is v of tau, so it's 20. And instead of using t, I'm going to be using tau. I change the variable so I can use t in the limit of the integral, e to the negative 10 of tau. Okay, and this one here is d of tau. And of course, the initial one here, I of 0, is just simply 0. So I don't have to write anything in here. Alright, so now this boils down to just simple 200 times the integral from 0 to t tau e to the negative 10 of tau d of tau. And of course we can carry out this integral. If you remember your calculus, this is just simply integration by part. So if you assume that u is just simply tau, that means d of u is just simply d tau. And of course if you assume that d of v is e to the negative 10 tau d tau, that means simply v is just negative 1 divided by 10 e to the negative 10 of tau. That's basically what we just did the integral. Alright, so now of course integration by part tells me that it's uv minus v times du. Okay, so let's just do this. I'm gonna say 200, the I of t is just simply 200 times uv, well u is tau, v is just simply that negative 1 divided by 10. Let me just do this here so I don't lose the negative, e to the negative 10 of tau, that's uv, minus v, which is simply negative 1 divided by 10 e to the negative 10 of t, or tau, and that's here is d of u, which is d of tau. And of course now the integration variable is just simply tau, and it was tau before anyway, so, and the tau went from 0 to t, so we have 0 to t in here. Alright, so we carry out the rest of it in here, and what we have is 200, and that's negative 1 divided by 10. And I believe this have to go from 0 to t anyway, so this will be, and I'll substitute all of these values in here, you'll see it in a minute. Okay, negative tau, e to the negative 10 of tau, and then this integral here is just simply positive 1 divided by 10, and this one here is just simply negative 1 divided by 10 e to the negative, I believe, 10 of tau, and that here is just simply from 0 to t. That's what we have to do. We just double check, and I think it's correct. So we just substitute certain values in here. We have 200, negative 1 divided by 10. I believe this should be, instead of tau, it will be t, e to the negative 10 of t. I believe negative 1 divided by 100, e to the negative 10 of t. Okay, and then here minus, well, this will be 0. Plus, I believe 1 divided by 10 times 1 divided by negative 10 here, e to the power 0, which is just 1. Okay, we substitute that here. I believe now we have 200. And then let's see here, can we take e to the negative 10 of t out? We can, and that will give us, and I think we can take the negative as well. That will give us 1 divided by that t plus 1 divided by 100. Okay, minus, well, let's double check what we have in here. We're going to multiply these two here, which is that 1 divided by 10, 1 divided by 10, and multiply by that. That will be 1 divided by 100. Okay, and I believe that's it. So we'll multiply by 200, we'll get negative 200, so negative 2e to the negative 10 of t. Actually, let me just take the 2 inside. I think will be just simpler. Okay, so e to the negative 10 of t. Okay, we're going to take it. 200 becomes 20t plus 2. That's what we have, plus 2 in here. That's what we have. Yep, and that will be in amps. So let me just read out this one here. So we'll copy this here. Okay, that will be the current. Let's copy in here. Let's paste it in here. That will be basically the value for that particular current. Let me just drag these down. Okay, so it doesn't interfere. And that will be the current for t is greater than or equal to 0 second, and that will be in amps. So I was able to figure out what the current value is. So now what we have to do is just figure out what the power is, and the power is just simply we multiply 0 times 0 is just simply 0, and then here times here, and of course we use positive because the passive sign convention. All I have to do is just multiply this value by this value and then figure out what the power is. Pretty straightforward. Yep, so you can probably do it on your own. So what's left? Well, what's left is here, the energy. So let's assume that I asked you to compute the energy. So all I have to do is just tell me half of L basically it's 0.5 times 0.1, which is 0.05. So that basically tells me it's W is just simply 0, and then it will be 0.05 times I squared, and the I squared is just simply this term that we just came up with, which is here, okay? And the whole thing is just basically square it. We just put it in here and paste it. I'll just make it a lot smaller, okay? And what we do is, all you have to do is just take it in here and just tell me that this here is squared. That will be basically the energy consumed. And you can clean this here. That will be for t is greater than or equal to 0. This will be for t is less than 0. So I went ahead and I computed all of these and I put it in a computer to draw these, and that's what we end up with. We end up with these equations. So just as a reminder, what we have is we had that voltage source in here. So we had this particular equation. So you can see that it actually reached some sort of a maximum and it goes down. And eventually at t equals infinity, you'll see that voltage actually drops to 0. And when t equals to infinity, you can think about this here. The current actually increases, and at infinity, this will be 0. This will be 0, so that leaves us with 2. So it actually approaches 2. And if you think about it, if the voltage is 0 and the current is 2 amps, okay, that means the current, that means this particular inductor, what happens is it stores energy and it keeps it at 2, so it never leaves this energy. And this is confirmed by looking at the power. If you look at the power, there's no negative. The power is also always positive, so it's always storing and consuming energy, and that's it. It never releases it. And you can see the exact amount of the energy being consumed by looking at it here. You'll see that it actually approaches the 0.2 joules in here, or 200 millijoules.